Welcome, everybody. I'm very excited to have you here today. I see a lot of people still coming in. Put on your headphones, yes, and we're going to get started. My name is Katja, and I'm a Senior Database Solutions Architect. I'm going to be joined later in the session by my colleague Sikandar. He has the same role as me. We work with customers on their database migration journey and also optimizing the database landscape in the cloud. We talk to customers a lot, and we hear them talk to us about their serverless architecture for applications, about their need to create always available applications that serve their customers in multiple regions as well. This is why last year re:Invent, we announced Amazon Aurora DSQL. And it's actually GA since last week, so perfect time to come to a session on this. We're going to start the session with an introduction on Amazon Aurora and its history. I'm going to move forward then to the DSQL architecture and also cover the components. We're moving forward then to transaction processing. How are we managing those? How are we scaling our underlying components to handle multiple transactions and also different workload patterns? We're then moving forward to design choices from DSQL. How did we build it up and why? And we're going to close not only with high availability, but also with a few tips and tricks for the developers in here, how to make the most out of the service. We are a customer-obsessed company, which means that we talk to our customers also a lot and we hear a lot about their challenges. I want to start with the functional ones. First one being scale. The limits, or well, let me say customers are constrained by the capacity limits per instance, which creates the need to right-size their workload and also manage cost effectively. I talk to customers on a day-to-day basis, and a lot of them also struggle with making sure that the demand is served by the current setup they have. The second one, well, you might have heard of the quote of our CTO, which says, "Everything fails all the time." Lower resiliency rates of traditional relational databases lead to unplanned outages, which can directly impact organizations' revenue. It's not only the functional challenges that customers are dealing with, it's the operational side of things as well. First one being the management overhead. Managing the infrastructure, right? Making sure you are taking a database offline for those patches and upgrades. And last but certainly not least is the complexity. From end to end, having the infrastructure set up and patched, the databases set up and configured in the right way, tuning the databases. And we're not only doing this for use cases today, but also for changing use cases and requirements of tomorrow. With all of this, let's move forward to Amazon Aurora, which we invented and launched because of all of these challenges, of course, also because of multiple other challenges as well. Can I see a raise of hands who here is using Aurora? Okay, I see quite a few. Very exciting and also not so surprising since we launched it over a decade ago. Amazon Aurora at the SQL prompt looks and feels just the same as any Postgres MySQL database, but under the hood it features a self-healing, fault-tolerant distributed storage system that can scale up to 128 terabytes. After launching Aurora, we continued with Aurora Serverless, which now added vertical scaling as well as and pay-per-use pricing. With Limitless, you now have the opportunity for horizontal scaling. It's a sharded architecture and offers support for distributed workloads. And the reason you're here today is Amazon Aurora DSQL. DSQL is an active multi-region distributed database. With DSQL, I want to start or highlight 4 key areas where it excels. And we're starting with the first, that DSQL scales compute independently from storage and read queries independently from write queries with virtually no limit. With DSQL, we offer 5 nines of availability in a multi-region setup, which means that you can build your always available applications in and across regions as well. DSQL also is serverless, meaning that there's no infrastructure to manage. You don't need to take your database offline, you don't need to patch and upgrade. All of this is handled behind the scenes by us. And last but not least, again, it's easy. You get 1 or 2 endpoints depending on the setup you have, and it's based on open source Postgres. You can get started with the service in just a few minutes. Then we have the DSQL architecture, because you might be asking yourself, this all sounds amazing, but how is it actually done? How can this be possible? Which is why I want to dive into the architecture, the components, and explain to you what we build up. We're starting with explaining that you can deploy DSQL in 2 ways. I mentioned before it's multi-region, but you can get started with a single region cluster. That's what we're starting with as well. In a single region cluster, you get 1 endpoint that you're interacting with, but the endpoint does offer you not only read or write, but both read and write transactions that you're handling with strong consistency. The multi-region cluster gives you an active database, which means that all components in this region can handle read and write queries as well. The cluster is distributed across multiple availability zones, with the storage being, or the data being replicated across 3 AZs. You don't have to provision any instances. Also with a single region deployment, the same for the multi-region deployment. And in total with this deployment, you are not just having an endpoint and behind the scenes multiple just standard Postgres instances, but it's fronting this distributed setup which I mentioned before. Single region deployments gives you 4 nines of availability. But wait a second, was I not saying 5 nines of availability before? Yes, I was, and thank you for listening. We get those 5 nines with a multi-region cluster. A multi-region cluster gives you those 5 nines of availability, and with that, the maximum application resiliency for multi-region deployments. You get 2 regional endpoints, and you just point your application to the right endpoint in your region. And both of those endpoints are fronting single logical databases that you're interacting with. And those still support concurrent read and write transactions with strong consistency also across those regions. In this multi-region setup, you might be seeing there's a 3rd region as well. And this 3rd region is called the witness region. The task of the witness region is to act as a tiebreaker in the case of a network partition, to decide which region gets to accept those rights. With that, the one more detail perhaps also on the witness region is that it itself does not have an endpoint or this underlying cluster. So its task was is to act as the tiebreaker. I want to take it a step further. We saw this overview of how a rough build-up of the regions look like, and we are now understanding the behind-the-scenes components of DSQL. It starts with the front end. The DSQL front end is what you connect to, and the DSQL front end provides you access and spins up or manages also those query processors then downstream that you connect with. The query processor is where most of your SQL execution happens, and it acts as dedicated Postgres engine for your transaction. The adjudicator is the element that decides whether a commit can be successful or not, and it communicates with other adjudicators to ensure isolation. The journal is then the point that makes a transaction durable and also replicates data across availability zones and across regions as well. We're moving forward to crossbar. Crossbar is the element that sorts your transaction in write order, and then storage applies the changes. Storage is also sharded based on your shard key. It provides the access to the data and also contains replicas of your data depending on the read workload. Looking at this, you see that we're splitting responsibilities in a relational database. I mentioned before, journal is responsible for durability, which is one very important concept for relational databases. And adjudicator is, for example, responsible for isolation. So you see we're splitting these out. And also, each of the components is supported by their own compute fleet, which means that they can scale independently and also horizontally. The query processor scales based on open sessions in your database. The adjudicator scales based on the shard key range. The journal and the crossbar, those scale with the commits. And storage also scales based on shard key. And it also scales the read replicas of the data based on your read workload. With that, we have a hopefully good first understanding of what the service is and the components. Good first overview. And we're going one step further. We're going to see now how transactions flow through this system, through these components. We're starting with a read transaction, and I want to use an example that hopefully everybody can relate to. So you guys are users, you're located or at the moment in Las Vegas, and you want to order a pizza. You don't just want to order any pizza, you want to have a pizza from a restaurant with a rating of 4.0 or higher. We're looking at the SQL statement for this. We're selecting star, so everything from the restaurant table, which has a rating equal or higher than 4.0. What happens behind the scenes? The client, the front end, connects to the SQL front end, which allocates a query processor for you. But before the query processor starts the execution, it reads its local clock. Clock or timing in general is one of the most important concepts behind DSQL, which is why we're going to spend just a few minutes. My colleague will spend just a few minutes later in the session on this. It reads the local clock, and then it assigns the time as the transaction start time. Now the read-only transaction begins. The storage is automatically and transparently to you as the user sharded based on shard keys. The query processor reads its local shard map to understand where the data is located, and then it accesses those storage nodes directly. One thing you might be noticing is that we're not consulting adjudicator, we're not looking at the journal, and we're not consulting the crossbar. Because with this read-only transaction, we don't need to look for any conflicts. We're reading the data on the system, so we don't need to involve these conflict-resolving components and making sure transactions are durably stored. One other thing you might be seeing or asking yourself is, what about cross-region, cross-AZ traffic? These things, so reading the data query processor, going to storage node and back, that's happening completely locally in the same region and the same availability zone that your query processor is located in. So optimizing also on that end. We're looking at the way back to the query processor. The storage nodes that we're retrieving the data from, they don't return pages, they return rows. Because we're supporting predicate pushdown, so all kinds of aggregating and filtering is done on the storage nodes, we're optimizing, first of all, on the way back, the amount of data transferred over the network, and also the amount of work that the query processor has to do. When we arrive back at the query processor merges all those results from storage nodes and returns the results back to the user. That's great for us. We have our four above-star restaurants. Let's continue. Going to make it a little more complex. We keep interacting with the front end. We are going to build up an interactive transaction. Work on the client, a little work on the database. We go back and forth a few times, and eventually we commit. Let's make it concrete again. We are searching for restaurants. We're browsing the menu of a restaurant we selected. We find an item. We're adding the item to our order, placing the order, and eventually we commit. In a traditional relational database, this would mean placing locks and doing checks on each transaction, each statement of this transaction. But DSQL acts differently. Because the query processor acts differently. The query processor acts as a holding tank for all the reads and also spooling all those writes locally. Once it's done, so once you're committing, and this is very important, on commit, this is sent to the adjudicator. The adjudicator is a component that will decide if the commit is successful or not. If it is successful, it will durably store that transaction on the journal. The crossbar will merge all those writes in right order, all the successful commits, and then storage will apply the changes. Remember the slide? When my colleague takes over, we're going to go deeper even, and we're going to understand more on the individual components as well. But I want to take a second to look at this from a different point of view. We're separating out the transaction into 3 different phases, basically. We're starting the transaction, we're starting the commit, and we're successfully committed at the end. We start the transaction with begin. And any of those selects and updates and inserts and delete, all of those happen locally. No inter-AZ, no inter-region traffic. I know I said it, but I want to highlight it again because this is so very important for that latency point of view. Then the commit begins. And on commit, you're getting added 2 round-trip times of latency, once per transaction, so not once per statement, once per transaction, and for read-write transactions only. This is only for those because we looked before at those read-only transactions, which don't do those conflict resolutions because we're only reading data. So those don't have that added latencies on commit. And in the end, the commit is hopefully successful, and this ends the full transaction that we just split into 3 phases. One thing I want to share, because this concept I learned something when I read the documentation on this a while back, is that it means that slow clients will not slow down the database. Because we're acting completely local with those selects and updates and inserts, and all of these are local, so a slow client will also just work locally until the point where it commits, and this is when it will impact the downstream system. But then all this slowness you might have experienced before is staying local and not impacting database performance. With that, I feel like we learned a lot on DSQL. We learned how the components are, we learned the different types of transactions and how they reflect on the database itself. And we're ready to go a step deeper, which is why I want to hand over to my colleague Sikandar, who's going to explain more details on the components. Thank you.
Thanks a lot, Katya, for introducing us into DSQL, talking about different architecture of both the configuration in single region as well as multi-region, and also talking about some of those components and how do they scale, right, at different levels. So folks, now it's time to dive just a tad bit deeper into understanding of those components, that how do they work when you are processing a transaction. So the first thing which comes to my mind is query processor, which is essentially the heart of DSQL. It does majority of the heavy lifting because that is where you are running your transactions. It runs inside something what we call as Firecracker VM, which is a micro VM, and it is hosted on bare metal. So when you connect to DSQL, we have hundreds or even thousands of these micro VMs available to handle your workload. And these query processors, they never talk to each other. They work in complete isolation. Talking about isolation, it's very important for a transactional database to decide which isolation level it is going to operate at. DSQL supports a snapshot isolation level, which is equivalent of repeatable read isolation level in Postgres. Some of you who have been working with Postgres may already have an idea about the repeatable read snapshot. What does it mean for DSQL perspective is that your transaction, it acts on a consistent snapshot of your database, which it existed at that point in time. And all the different statements in that transaction, they read through that consistent copy of the snapshot. My colleague Katya mentioned that query processor acts as a holding tank for your transaction. And it does not immediately apply those inserts and updates down to the storage. Instead, it spools them locally. In a way, we can also call it that it is providing a private workspace for your transaction. And it also provides you with read your write capabilities. That is, the statements or subsequent statements within a transaction can read those pending changes which were made by earlier statement. So nice capability, right? But we are not done yet. We have to commit the transaction as well. And in Aurora DSQL, it is the responsibility of the adjudicator to decide whether a transaction can be committed or not. Adjudicator is the component which sits in the right path of the query. It detects, and then it resolves those conflicts as well. Let's see how that works under the hood. But before we go down deeper into adjudicator, let's try and understand about another very important element in Aurora DSQL, which is time. So we have two important timestamps to worry about, which is tstart, the start time of your transaction, and tcommit, which is the committed or the commit time of your transaction. Why it is so important or why time is very important in a distributed database? Because as my colleague mentioned, that there are multiple components in database, in a distributed database like DSQL, which are spread across different AZs, different regions. And all of those components have their own local clocks. So we need to find a way so that we can synchronize all those local clocks. And in order to do that, we use Amazon Time Sync service, which acts as a global satellite clock, highly synchronized, and it helps us to basically synchronize all those local clocks of those distributed components with microsecond precision. And with the help of time sync, we can finally trust these two timestamps. Coming back to adjudicator, right? So query processor creates what we call as a payload, which consists of information to the adjudicator to decide whether a transaction can be committed or not. That payload consists of three important things, which is start time of the transaction, or T-start, the write set, or the keys which it intends to write, the post image of the records which it is trying to change, and how they're going to look like once the changes are applied. So these changes or these information is called as payload, which QP creates. QP and adjudicator, they are friends. They do not talk often, but if they have to talk, this is how the conversation will go. So QP will say to the adjudicator that, my dear friend adjudicator, these are the keys I intend to write, and here is my T-start time. If no other transaction has written down these keys since T-start, then please pick up a T-commit and make my transaction durable. And also, once you have made my transaction durable, please do not allow a lower T-commit for any other conflicting transaction. So this is just a simple mechanism which QP and adjudicator works with on a handover basis. Now, we are talking about a distributed system, so there could be a scenario when there are conflicts. How DSQL or how adjudicator is going to handle those conflicts? Let's take an example of two transactions, transaction A and transaction B. In this example, both these transactions are starting almost at the same time. But transaction A is going to commit just a tad bit sooner. And remember, we can trust that these timestamps are highly synchronized between all the distributed components because of Amazon Time Sync. Let's see an example where we have conflicting transactions, right? These two transactions, transaction A and transaction B, both of them have reached to adjudicator stage. And now adjudicator will compare the payload and the T-start time for these two transactions. And it finds out that both these transactions are trying to update the same record, which is ID number 3 here. DSQL is only going to allow, at this point, to proceed or to commit one transaction out of these two. The transaction which is going to commit first. And the other transaction, which is transaction B, is going to be aborted. But what happens when there are no conflicts? If those two transactions, A and B, does not have any conflicting rights, then adjudicator is going to commit those transactions individually. It is going to proceed committing both these transactions. So adjudicator has finally decided which transaction it needs to commit and which needs to be aborted. But what makes your transaction durable? In traditional relational databases, the way it works is that storage is responsible to make those changes durable. So unless the changes are written down at the storage layer, you cannot say that your transaction is committed. So storage layer plays the main role or has the responsibility to maintain durability. But this model comes with a cost, because you are doing a lot of checkpointing, you are doing a lot of logging, and along with that, you are also waiting or wasting some resources to synchronize the buffer cache and storage. In DSQL, this complexity is managed at the level of journal. What is journal? Journal is an internal component which we have been using with other AWS services as well. And this is optimized for data replication across AZs as well as across regions. Journal maintains an ordered stream of committed transaction. And once your transactions are written down to journal, you can consider them that they are finally committed and durable. Similar to other components of DSQL, journal also scales horizontally, and transaction or adjudicator can write those committed or commits to any journal. There is also a supplementary component involved, which is called as crossbar. In traditional databases or in relational databases, I must say, everything has to follow an order. It is the responsibility of crossbar to pull those changes from the journal and send it to the storage in an ordered sequence. So now let's have a look at the complete end-to-end transaction. So once adjudicator decides that your transaction can finally be committed, it sends the payload as well as tcommit to the journal and finally make your transaction durable. Once journal acknowledges the write, it will send a success code back to the query processor, and from there, back to you. In the background, crossbar will start pulling those records and will send those records in an order sequence to the storage. And at that point, from your perspective, the transaction is complete. While designing a distributed architecture of Aurora DSQL, we had to make some design choices as well. And I wanted to discuss some of those design choices, that what was the reason behind those choices that we took when we were architecting Aurora DSQL. The first thing is, it is not snapshot isolation only. It is strong snapshot isolation. That is, when you are writing anything to the database, you can immediately read that change from any of the regional endpoint, even if it is cross-region. You are getting strong consistency across multiple regions. That's why it is strong snapshot isolation. It helps the developers to develop those applications which behaves reliably. The second design choice that we took is about the concurrency control. Concurrency control is a very essential topic when it comes to relational database. Why? Because it allows you to run multiple transactions against your database without worrying about data corruption or data inconsistency. Traditional database typically uses pessimistic approach. That is, they are running a transaction, and it is locking the rows which it intends to change. That lock sometimes may be there for indefinite amount of time, and sometimes it may even run into deadlocks. Aurora DSQL uses optimistic concurrency control, where we are not taking locks when we are running a transaction. The locks upfront are not acquired with optimistic concurrency control. And if you remember, we talked about query processor, where we are spooling all the inserts and updates locally first, and we are only sending it over to adjudicator at the time of commit. So that's why there is very little cross-region chatter as well, right, when we are using optimistic concurrency control. Another good thing about optimistic concurrency control is that it is highly deterministic. You will come to know at the very moment when your transaction is aborted, and you can take an immediate action. So it helps the developers in certain ways, but at the same time, it also requires developers to think about some new patterns, which we're going to discuss in upcoming slides as well. And the last design choice, which I would like to talk about here, is that Aurora DSQL is PostgreSQL compatible. That is, it is built on the top of your favorite PostgreSQL version 16, and it has its dialect, parser, planner, type system, and the wire protocol. Even the drivers and the tools which is supported with PostgreSQL, they're also compatible with Aurora DSQL with minor or no configuration change at all. For developers, it means that if you are running a query with your PostgreSQL database, and then you run the query against Aurora DSQL, you will get a similar output. All the SQL features are supported here in DSQL as well, such as you're doing select operations, joining, indexing. All those things are available here as well. So we have looked into different components. We have dived deeper into those components as well. We understood what are the different architecture patterns or different architecture configuration options of DSQL. Another important thing with DSQL is about resiliency. Let's talk about that how it provides that high availability out of the box. So this snippet is basically giving you a logical view of internal application stack of DSQL. A DSQL cluster is spanned across, or a multi-region DSQL cluster is spanned across 3 different regions. You have region A and region C as primary. And you also have a region B as a witness region. Region A and region C provides you with regional endpoints, which you can use with your OLTP applications. However, region B is journal-only witness region. It is there to ensure that a quorum is maintained in the event of a failure of a region or a network partition. Another good property of this journal or witness region is that if you have a cluster configuration which is spanned across wide geography, you can put this witness region somewhere in the middle for better commit latency. But you cannot connect to this witness region. Only 2 endpoints are available to you, which are in region A and region C. Also, Aurora DSQL is optimized for fast failovers. Let's see what happens in case of a network partition. In this example, we are assuming that you are not able to reach region C for some reason, right? What happens? How does it behave then? So the first thing it is going to do is that journal is going to stop replicating to the failed region. Now, the replication of data has stopped completely. And in DSQL, normally there is no leadership. However, adjudicator still maintain a leadership, but that is a very soft transient state leadership, right? Which can be recreated if required. Essentially, it means that an instance of an adjudicator is responsible for a given set of keys. And in the scenario of a failure, like here, region C, we are not able to reach, we need to move that leadership from unhealthy region to the healthy region, which we can do quickly because it only maintaining soft transient state. It does not take too much time. Once the leadership is moved from unhealthy region to the healthy region, you can no longer connect to the endpoint of the unhealthy region. Region C is completely unavailable for your application. But region A will continue to work. Your application in region A will continue to work as it is, and the database will always be strongly consistent and durable in region A. You can also repoint your application, which are working in region C, to region A with the help of maybe Route 53, some health checks, and so on. We have looked into the components. We have looked into some of the features it has to offer. Let's also talk about some of the best practices that a developer needs to keep in mind while developing an application around DSQL. The first recommendation or best practice is to have an understanding that Aurora is built for OLTP. It is not optimized for analytical workload. That is, it is not optimized to run those big aggregation or complex sorting. Second is, if you remember, I talked about OCC, optimistic concurrency control. It is deterministic and helps the developer in stop worrying about few things. Do not have to wait indefinitely when there are locks. but it also means that there could be a scenario in which a conflicting transaction may abort. And in that case, you need to retry that transaction again. So have that mindset of baking in that retry logic into your application when you are developing with Aurora DSQL. Another thing is that you should try and avoid hot write keys. What does that mean? When you have concurrent transactions and when those transactions are trying to update the same record, then this situation will arise. And in Aurora DSQL, as we have seen, that only one transaction or only one conflicting transaction will proceed to commit, and the rest are going to be aborted. So essentially, in Aurora DSQL, you should have your data spread across key space as dispersely as possible. Right? And the reason behind that is when you have too many conflicting transactions which are getting aborted, then it means that you need to retry them again and again, which is going to then impact the throughput of your application. And the performance is going to suffer. So try to spread out the key space as much as possible. And along the similar lines, also avoid hotkey ranges. If you talk about traditional relational database, they love data locality because mostly they have a small working set which can be pulled in from the storage, and your queries can be served out of memory, which works great for single instance system, right? When you have a single writer. But for a distributed database like Aurora DSQL, you need to disperse your data as much as possible so that you can get a better performance. That's why some of the things like UIDs or compound keys, using those works better than using sequential IDs. This is all I wanted to cover from this slide, from this session. We also have tons of resources available which can get you started on Aurora DSQL. The database is generally available since last week, so we cannot wait for you to start building those applications around it. And also, please provide your feedback that how do you feel working with Aurora DSQL. Also, don't forget to fill out the session survey. It'll hardly take a few seconds of your time, but it'll give us great insights. And if you have any more question, either to me or to Katya, you can find us at the database booth, and we'll be more than happy to take up any questions that you may have. And with that, I would like to thank you for your time. Enjoy your time at Summit.